In 1874, a German mathematician wrote down a list containing every real number between 0 and 1. Then he wrote down a number that wasn't on it. It took him about 4 lines. Here's the list. First row, 0.14159. Second row, 0.71828. It goes on forever, and it's supposed to contain everything there is. Now walk the diagonal, taking the first digit of row 1, then the second digit of row 2, and so on down. 1822. Add 1 to each digit. 2933. That new number differs from row 1 in the first place, from row 2 in the second place, and from every row forever after. It cannot be on the list. This should have been impossible. Infinite meant one thing back then: you could pair it off with the counting numbers. The fractions submit to this beautifully. Zigzag through them, and every single one gets a number. There are as many fractions as there are whole numbers, which already sounds wrong and is true. Reals refuse. No list can hold them. There are at least 2 different sizes of infinity, and the second one is bigger than counting. Mathematics did not take this well. Leopold Kronker had said God made the integers, and everything else was human invention. He blocked Cantor's publications and called him a corrupter of youth. Poincaré called set theory a disease that mathematics would eventually recover from. Cantor spent the rest of his life cycling in and out of the nerve clinic at Halle. Hilbert defended him in one sentence: "No one shall expel us from the paradise Cantor has created." Now strip the decimals away. Rows are candidates, columns are properties. Flip the diagonal and you've built something that differs from every candidate you listed. That's not a fact about numbers. That's a machine, feed it any list, and it hands back something the list missed. In 1901, Bertrand Russell pointed it at sets themselves, asking us to consider the set of all sets that don't contain themselves. Does it contain itself? Either answer is wrong. Gottlob Frege received this in a letter while the second volume of his life's work was at the printer. He added an appendix admitting the foundation had collapsed. So mathematics decided to rebuild on solid ground. Hilbert's program, the 1920s. Axiomatize everything, then prove the system complete and consistent and mechanically decidable. We must know, he said. We will know. But notice what a proof actually is: a finite string of symbols, which means proofs can be listed. Kurt Gödel was 25. He found a way to turn every mathematical statement into a number, so statements could talk about statements. Then he ran the diagonal, building a statement that says, "This statement has no proof. If it's provable, it's false, and your system proves falsehoods. If it's unprovable, then it's true, a true thing your system can never reach." Then he proved something worse. No consistent system strong enough for arithmetic can prove its own consistency. 20 pages finished Hilbert's program. In 1936, Alan Turing did it again. Programs are finite strings, so programs can be listed. Now suppose something could read any program at all and tell you whether it halts. Turing built a program that consults that oracle about itself and does the opposite. It's the digit flip from 4 minutes ago, wearing a costume. That's why no antivirus catches everything and no tool finds every bug. Nothing broke. Look back at point 2933, the first object anyone ever proved was out of reach. Cantor's own question about the sizes of infinity turned out to be unanswerable inside the rules. Not too hard. Independent, the axioms simply don't decide. Any system strong enough to describe itself contains truths it cannot reach, and that's not a gap in our knowledge. It's a theorem. Cantor died in a sanatorium in 1918, still defending a number nobody could reach. The number is still there, so is everything it broke.